Welcome to this video on polymer feedstocks for additive manufacturing. Today, we will explore the relationship between material chemistry and its impact on printability and properties in material extrusion and powder processes. I am Kunal Dewangan, a research scholar at the National Institute of Technology, Raipur. This video establishes the foundation of polymer science within the context of additive manufacturing. Our key objectives include understanding polymer chemistry, analyzing process dynamics like molecular weight and melt flow, and applying material forensics to assess how processing history impacts the properties of final parts. Additive manufacturing depends heavily on polymer thermal transitions. Unlike injection molding, these processes involve localized heating and rapid cooling gradients, making macromolecular structure and chain entanglement vital for predicting potential failures. Next, we examine the fundamental differences between two main types of thermoplastics used in printing: amorphous and semi-crystalline polymers. Amorphous polymers have a random structure and soften gradually above their glass transition temperature. In contrast, semi-crystalline polymers contain ordered, folded chains that produce a sharp melting point and distinct mechanical properties. In an amorphous structure, polymer chains are entangled without long-range order. This state allows for a transition through a rubbery, viscous phase and generally results in lower volumetric shrinkage during cooling. ABS is a classic amorphous terpolymer known for its toughness, while polycarbonate is a high-performance amorphous polymer with an exceptionally high glass transition temperature, requiring strict thermal control to prevent warping. Amorphous polymers are favored for high-dimensional accuracy, as their shrinkage rate is typically under 1%, and their broad softening window promotes excellent inner-layer adhesion. Semi-crystalline polymers feature complex microstructures called sphericity. As these chains fold into dense configurations during cooling, they release latent heat, which leads to significant volumetric shrinkage and presents challenges for dimensional stability. We see different profiles for these materials. PLA is a low-temperature semi-crystalline polymer, polyamides like PA12 offer high toughness, and PEKK is an ultra-high-performance material requiring precise thermal management. Crystallinity kinetics are largely driven by the cooling rate. Rapid quenching can create smaller spherilites or even amorphous structures, while slower cooling increases stiffness at the cost of higher shrinkage. The Avramey equation is used to model these crystallization kinetics. It factors in relative crystallinity, the temperature-dependent rate constant, and the Avramey exponent, which relates to crystal growth dimensionality. Bed adhesion is managed differently for each. Amorphous polymers are best printed near their glass transition temperature, whereas semi-crystalline polymers require higher bed temperatures to mitigate the effects of rapid volume reduction. This concludes our overview of material extrusion, filament chemistry, and the rheological principles governing these printing processes. Now let's turn our attention to the core requirements for successful material extrusion. Key factors include maintaining a consistent filament diameter, controlling moisture, and optimizing viscosity to ensure reliable extrusion. Molecular weight is the primary driver of polymer properties. Higher molecular weight improves strength and toughness through chain entanglement, but significantly increases viscosity, which complicates the extrusion process. When molecular weight exceeds the critical entanglement threshold, physical entanglements form, providing essential material strength. Thermal energy during extrusion allows these long, entangled chains to move past one another. Interlayer adhesion is a common challenge in material extrusion. Achieving a strong bond requires maintaining the interface above the glass transition temperature, allowing polymer chains to diffuse across the layer boundary. The melt flow index, or MFI, serves as a standard measure for the flow characteristics of a thermoplastic polymer under specific temperature and weight conditions. Polymer melts generally demonstrate shear thinning behavior, where viscosity decreases as the shear rate increases. This is critical for predicting how the material will flow through a small print nozzle. Many engineering polymers are hygroscopic, meaning they absorb water from the air. This moisture can be detrimental to the printing process, leading to defects like foaming and poor surface finish. When moisture is trapped in the polymer, it causes hydrolysis during the high-temperature extrusion phase. This process cleaves the polymer chains, dramatically reducing molecular weight and causing severe structural weakness. To maintain material integrity, proper drying of hygroscopic polymers is essential before they reach the extruder. Drying cycles must be strictly followed to protect the polymer backbone. We will now shift our focus to powder bed fusion, or PBF, discussing the role of polymer morphology and the reusability of powders in processes like selective laser sintering. Polyamides like PA11 and PA12 dominate the PBF market due to their excellent thermal windows, while TPU is widely used for flexible, rubber-like parts and complex lattice geometries. PA12 is the workhorse of the industry. Its effectiveness lies in its wide supercooling window, which allows for stable operation in the powder bed while enabling precise laser sintering. High-performance materials like PEKK and PEKK offer superior mechanical and thermal properties, but require specialized machines capable of maintaining temperatures near 300 degrees Celsius during production. Thermoplastic polyurethanes allow for energy-absorbing structures. However, preparing these materials for PBF is challenging, often requiring cryogenic milling to achieve the correct powder characteristics. Finally, powder morphology is crucial. Highly spherical powders behave like small ball bearings, ensuring smooth, uniform distribution in the powder bed, which is vital for achieving high-density parts. Moving on to powder quality, we focus on flowability. Devices like the Revolution Powder Analyzer or a Hall flow meter help us assess this. The avalanche angle is a key metric. A lower angle indicates better flow. If flow is poor, you get short feeds, and nanoparticle flow agents are often used to improve the performance of non-spherical powders. This image illustrates the typical particle size distribution for standard SLS-PA12 powder. Achieving the right distribution is essential for consistent packing and sintering. The particle size distribution is a balancing act. Particles that are too fine under 20 microns clump and cause dust, while particles that are too coarse over 100 microns result in poor surface finish and weak mechanical properties. Finding the ideal range is critical for successful printing. Success in powder bed fusion depends on the sintering thermal window. This is the temperature gap between crystallization onset during cooling and melting onset during heating. The printer must keep the powder bed precisely within this range throughout the build. During a print, the unsintered powder stays hot for extended periods. This heat exposure, combined with trace oxygen in the chamber, leads to thermo-oxidative degradation. In PA12, this causes polymer chains to cross-link, which increases viscosity and ruins the powder's potential for future reuse. To combat this degradation, we use a refresh strategy. By mixing about 30 to 50% of virgin powder with the used material, we dilute the high-viscosity cross-linked polymer. This brings the average melt flow index back into a printable range for the next cycle. Now, let's explore filled and composite systems, where we modify basic polymer properties using additives to enhance the performance of the final parts. Fillers serve two main roles: mechanical enhancement and introducing functional properties. By adding reinforcement, we can increase stiffness and strength. Additionally, specific fillers can turn insulating polymers into materials with conductive or magnetic properties. Carbon fiber composites are a prime example. Short, chopped fibers significantly increase stiffness and reduce thermal warping. However, they also introduce anisotropy because the fibers align with the extrusion path and are highly abrasive to printer components. Glass-filled systems are also common. While they provide excellent thermal stability and stiffness, they do increase the density of the printed part. It is important to remember that these materials can become more brittle than the base polymer, affecting impact resistance. For specific electronics applications, we use metal-filled polymers. These are loaded with copper, silver, or graphene to allow for conductive pathways. Reaching the necessary percolation threshold often requires high loading, which can unfortunately compromise the material's printability. Working with composite filaments also changes our rheology. The fillers increase apparent viscosity, often necessitating higher print temperatures. They also accelerate nozzle wear, so using hardened steel or tungsten carbide nozzles is a standard requirement. In this final section, we shift to practical laboratory demonstrations, where we translate these theories into empirical measurements. Our lab protocols focus on three key areas: verifying filament diameter for consistency, drying materials to prevent hydrolysis, and mechanical testing to understand how these factors affect the strength of our printed components. To wrap up, remember that even small variations in filament diameter have a major impact. Since slicers calculate volume based on the area of the filament, even a slight increase in diameter can lead to significant overextrusion and dimensional inaccuracies in your parts.